We're very happy to have Silviu Pufu with us this week. He'll give a series of lectures on gauge gravity duality. That's another method, a rather miraculous method for studying some strongly coupled gauge theories in addition to lattice and generalized symmetries and other things that we heard about. So please, the first lecture.
All right. As Igor said, I'm going to talk about the gauge gravity duality, and I was asked to start with an introduction to the gauge gravity duality. So the stuff I'll talk about today will be relatively old, but after seeing the previous lecture, maybe not as old. I put up some references there, the original papers, and well, many people have lectured about this, and here are references to some TASI lectures by various people. So the gauge gravity duality is a duality between gauge theory in d-dimensional space-time and gravity in at least d+1 dimensions. It's not any gauge theories. The gauge theories have various properties. One of the properties is that there are many degrees of freedom, sometimes referred to as large n. They're also strongly coupled, so strong coupling. And in the cases that are most well studied and best understood, they're also supersymmetric, but that's not believed to be an essential part of the duality. And also the gauge theories, also in the cases that are best understood, are conformal field theories and deformations of conformal field theories. So CFTs or deformations of CFTs. But again, I can generalize away from that. The essential parts are many degrees of freedom and strong coupling. Those really are important. And they're important for having gravity on the other side. Many degrees of freedom for the gauge theory translates in the gravity description being semi-classical. So in other words, if we think of it in terms of fields and diagrams, loops would be suppressed. So loops are suppressed. Strong coupling translates into having a regular gravity theory with two derivatives. So two derivative Lagrangian. So higher derivatives in the Lagrangian would be suppressed as well. And I'll explain later in this lecture series how to go beyond two derivatives to more derivatives and what one can learn about that. If the gauge theory is supersymmetric, then the description in terms of gravity is in terms of supergravity. When we're talking about CFTs or deformations of CFTs, this means on the gravity side that we have asymptotically anti-de Sitter backgrounds, anti-ADS. I'll explain what ADS space is in a bit. So, yeah.
Also, you took the sparsity of light spectrum of CFT operators on the left-hand side of the requirement.
Yes. these are some general features. I'm not claiming this is a complete list. Indeed, because gravity has spin up to 2, it must be that on the gauge theory side, if we have operators with spin bigger than 2, I'll explain maybe in the next lecture, that are single trace, then they have to have very, very large dimensions. So try to put that higher. It's a disaster already. Okay, so as an example, I just wanted to draw 2 pictures. So one picture that one can have in mind would be like this. So this would be the case where the field theory, the gauge theory would be on, so the QFT on flat space, so RD comma 1. And the other example, so in this case, the field theory would be in, sorry, RD minus 1 comma 1 to have D dimensions total. In D dimensions, and then gravity is in the space with 1 dimension higher. And I'll explain what the space is in a bit. So here, there would be an extra direction. I'll call Z. And another picture to have in mind is, the QFT doesn't have to live, the gauge theory doesn't have to live in flat space. It could live, for example, on a sphere times time. So a picture to have in mind is something like this. So this would be for a QFT on SD minus 1 times R. So this is time. And in both of these cases, we can think about the QFT as living on, in a rough sense, we can think of it as living on the boundary of the space. But it's described, it can be described by gravity in the bulk and the entire space. So this would be here, well, I wrote down QFT on SD minus 1 cross R. So these are spaces into the Sitter space. I'll write down what it is in a bit. This would be an example of a space in the bulk. And it's got some properties that I think it's useful to keep them in mind for, starting now, before I write down the specific metric. So one property is that the boundary of the space, so the boundary should be identified with the space where the QFT lives, is at infinite proper distance. So these spaces are very big. However, light rays or null geodesics can reach the boundary in finite time. And to study a theory like this, we have to impose boundary conditions at the boundary of the space. So impose boundary conditions. So, and what that implies, so boundary conditions on the boundary, what that implies is that the observables of this theory, we can define a set of observables that are defined on the boundary. Okay, so these are rough, very rough features of these spaces with boundaries that are very far away. So a most studied example of gauge gravity duality is a duality between, where on the gauge theory side, we have gauge theory in 3+1 dimensions called n equal 4 super Yang-Mills, supersymmetric Yang-Mills theory. I'll say more about it later. So in 3+1 dimensions. And the gravity is actually gravity in 10 dimensions. It describes fluctuations around a 10-dimensional space-time, and that 10-dimensional space-time is AdS5 times S5. And it's a background of type 2B string theory. Of course, I'm not expecting people, since this is an introduction, I'm not expecting people to already know what this is. But I just wanted to mention it because just to show that there exists at least one example where this kind of idea, where gauge theory can be described by gravity in a space with at least one more dimension. There exists at least one example where such an idea works. Okay. So you might ask, why would we, if we're interested in solving QCD, as we should be, why would we worry about, why would we want to know about AdS-CFT? So one complaint one can have is that, well, QCD, the theory we're interested in studying, is not conformal, of course. And it's also not supersymmetric. So why would we want to study conformal field theories that might also be supersymmetric? And the answer to that is that, well, there's several answers. One answer is that we might be interested in studying more generally the space of all quantum field theories. And in the space of all quantum field theories, conformal field theories are good starting points. One can start with a conformal field theory, and then one can deform it. And one can deform it in different ways. For example, if we have a theory with some fields, we can introduce some masses for those fields, or we can make some other relevant deformations of those conformal field theories. We could study within a given theory that could be conformal and could be supersymmetric. We could study states that break conformal symmetry or supersymmetry. And maybe the properties of those states would not rely so heavily, because conformal symmetry and supersymmetry would be broken, the properties of those states would not rely so heavily on conformal symmetry and supersymmetry. And of course, there's examples, n equal 4 super Yang-Mills, this example that I gave here has a lot of supersymmetry. There are other examples, and Igor will mention that in his talk later this afternoon. There are examples with less supersymmetry that look more like QCD. So that's one reason. So the summary is that we can start with a CFT and we can deform it to get a more realistic theory. And the other reason why it would be good to study AdS-CFT is that, well, it is a method that describes strongly coupled gauge theories. So we can try to use it to learn about strongly interacting gauge theories when other methods are not that helpful. So learn about perhaps general features, if we can, of strongly coupled gauge theories. Okay, so that's my very rough, very roughly the motivation. So now let me describe what entity de Sitter space is. So yeah, maybe I can do it here. So AdS in d+1 dimensions. One can think of it as a codimension 1 surface in a bigger space. And that surface is given by something that looks like a hyperboloid. So we have minus x0 squared plus x1 squared plus x2 squared plus x3 squared all the way to xd squared minus xd plus 1 squared is equal to minus L squared. It's a constant. So it's this surface, ADS space is this surface embedded in a space-time with d+2 dimensions. So this means that the space is d+1 dimensional. Oh, sorry, it's R. It's in space with d+2 dimensions, but with signature with 2 negative directions, 2 time-like directions, and 1 space-like direction. So with signature that matches the signature in this quadratic form in the definition of the hyperboloid. So minus, and then all pluses, and then the last one is minus. Is it clear what the space is? So it's just this surface embedded in RD comma 2. You can draw it as a hyperboloid. Okay. So it looks like this. Here, this is the axis. So the directions that are marked are this is x0, this is xd plus 1, the time-like ones. And here, these other directions are all the space-like ones. So x1 through xd. Sorry, maybe I should have said that it's a curved space. This is L is the radius of curvature. It's negatively curved. And L is the radius of curvature. Now, there's one small problem with this picture here. And the problem is that these are the 2 time-like directions. So if you go then around the hyperboloid over here, this is a closed time-like curve. So then ADS space, global ADS space is taken to not be the hyperboloid, but to be the covering space of the hyperboloid so that it doesn't have closed time-like curves. So this would be, there's a closed time-like curve. Which implies that what's called global ADS is the covering space of the hyperboloid. So essentially we'll unravel this hyperboloid. We parameterize it with some coordinates, and then some coordinate t here will be periodic, and then instead of having t periodic, we just make t run over the entire real line. Okay. Good. So there's various coordinate systems one can put on anti-de Sitter space. I will just focus on one. And that coordinate system, I wrote it down over here. So I have to come up, so coordinates. I have to come up with d+1 coordinates. So one of them would be time. The other one would be xm, the space coordinates. M goes from 1 to d-1. And then another spatial coordinate I'll call z. So in total, d+1 coordinates for d+1 dimensional space. And the relation between these coordinates and the x's is given on the right board. So x0 is LT over z, x1 through xd-1 are L times xm over z. Xd is given by this more complicated expression, and xd+1 is also given by that more complicated expression. The difference between them is just a minus sign. What property should this parameterization obey? It should satisfy this equation. So the claim is that if you plug in, it's not obvious, if you plug in that expression into that equation, it's satisfied. So then we can obtain the metric in those coordinates from the induced metric, which is flat on Rd, 2. And the metric in these coordinates is very simple. It is L squared over z squared times minus dt squared plus dx squared, the usual metric in Minkowski space, minus dt squared plus dx squared, and then there's an extra plus dz squared. Okay. So it's like the picture I had over there, where there's an extra z coordinate that starts at 0. So z here, z is positive. There's some other coordinates that parameterize Minkowski space, but there's a non-trivial factor in front of the metric, which is in this case L squared over z squared. Okay. So, by the way, these coordinates do not parameterize the entire covering space of the hyperboloid. They actually don't even parameterize the entire hyperboloid. They parameterize only half of the hyperboloid. How do we see that it's only half? Well, look at these expressions here for xd and xd+1. And if we add them up, we get L squared over z, which is positive. So the last two coordinates are positive, but for the hyperboloid, there's no restriction on what the fact that the last two coordinates should be positive. So parameter is only half. Okay. Good. So these coordinates are good for describing CFT it's like the picture over here. So the coordinates are good for describing a CFT that lives on Rd-1, so in Minkowski space. Hopefully the rough picture is clear. There's a CFT that lives in Minkowski space and described by gravity in one space of higher dimension, and the space of higher dimension has an extra coordinate z. And the metric of that space is that. Okay. So let me mention some properties. Well, not many, just a few. The first property is that the isometries of ADS space correspond. We can see them very clearly from this definition in terms of the hyperboloid that's embedded in this space. We can make, if we make any Lorentz transformations in Rd, 2, those would change the x coordinates, but this equation would stay invariant. So those are the symmetries. It's just the Lorentz transformations and space with d plus 2 dimensions of signature d comma 2. So those are SO d comma 2. And they're described by the change in the coordinate xi is epsilon ij xj, like the Lorentz transformations are in 3 plus 1 dimensions. So these preserve, make transformations like these which preserve eta ij xi xj. One important fact about ADS-CFT is that this isometric group of ADS space is the same as the conformal group, the symmetry group of a conformal field theory. So as an example, I mean, there's sort of trivial examples. If we make Lorentz transformations in the first d coordinate here, then that would be the same as making a Lorentz transformation in the t and x, t and little x coordinates. So those would be, those are part of the isometries. A more non-trivial one is where we take xd plus xd plus 1, and we send it to, say, 1 over lambda and xd plus xd plus 1, and xd minus xd plus 1, we send it to lambda and xd minus xd plus 1. And in terms of our parametrization, this is t goes to lambda t, x goes to lambda x, z goes to lambda z. So it's like a dilatation as far as the t and x coordinates go. But of course, a dilatation in 4 dimensions or in any number of dimensions is not a symmetry of the metric. The metric changes. However, in ADS, because there's this extra z, if we supplement it by z goes to lambda z, then the entire metric stays unchanged, which means this is an isometry. Okay. So that's one property. Another property is that this is a space of constant negative curvature. That's probably, hopefully not hard to believe, because if we just change some signs here, if we made all the signs plus, then we'd get a sphere, and the sphere has constant curvature. But because we changed some signs, instead of a curvature being positive, it's now negative. So constant negative curvature. So the Riemann tensor is -1 over L squared, is G mu rho, G nu sigma minus G nu sigma G nu rho. For a sphere, the same formula holds, but with a plus, and L would be the radius of curvature. And the third property, and last that I'll mention, is that this is a solution of Einstein's equations with negative cosmological constant. So if we were to write down the action for gravity with a negative cosmological constant, so 1 over 16 pi g, g is the Newton constant, times integral over d plus 1 dimensions. It's minus g here, r minus 2 lambda, where lambda is minus d times d minus 1 over 2L squared, has this specific value. Then de Sitter space of radius L is a solution of the Einstein equations that follow from this action. Any questions about anti-de Sitter space. Okay. Either super clear or totally incomprehensible. Maybe leave that there. Maybe we'll need those coordinates later. Find an eraser. Okay. So now, why is this relevant? Why do we have to solve? Yeah. Over here, you mean, or in which equation? In which equation? Then it wouldn't be anti-de Sitter space. It would be some other space. But we can have there examples of gauge gravity duality where the space is asymptotically ADS. So close to the boundary, it approaches more and more anti-de Sitter space, but away from the boundary, it's no longer anti-de Sitter space. And that can sometimes, well, that it can be understood as deformations of the conformal field theory. Any other questions? So that case is also relevant. It doesn't have constant negative curvature. Okay, so anti-de Sitter space, the reason why it's important for gauge gravity duality is that it appears in string theory. To explain that, well, one would have to explain what string theory is. I don't want to do that. So I'll just say some roughly where it comes from. Okay, so string theory is a theory of strings, relativistic strings. Let's add more information. Right? Relativistic strings. Strings have a string. What are the parameters? Well, if we have strings, we have a string tension, right? So the parameters are string tension. Which is denoted by 1 over 2 pi alpha prime. So essentially, if we have a string world sheet, then the action is 1 over 2 pi alpha prime, the tension, times the area. So that's one feature of string theory. And I think of all people, and people who attend school on QCD, for them, maybe this shouldn't be that crazy, but there's a string tension. Okay, so, and then alpha prime, we can also write it. So alpha prime has dimensions of length squared. So we can also write it as string length squared, where this is the definition of the string length. So string length is just the square root of alpha prime. And strings also have, well, they could also interact, and there's a string coupling. So that's denoted by G string. So it describes this process where the string just splits into two. Okay, that's all we need to know about string theory. Well, almost. So the strings, there's a quantum theory, the strings move in space-time. We can quantize them. If they're the lowest few modes, for the lowest few modes, the strings are very small, so they look like particles. So one can ask, what is the spectrum of particles? So excitation spectrum of closed strings. So we have particles of various masses. Question, based on what I said so far, of what order should the masses be by dimensional analysis? 1 over the, not the coupling, the string length. Energy has the same dimensions as 1 over length. So the masses should be of order 1 over the string length. But then what happens in the superstring theory, it's indeed true that most masses are of order 1 over the string length, but some of the particles are massless. So there's massless states and massive states, with the masses of order 1 over the string length. So whenever we have massless particles and massive particles, if we go to very low energies, we can forget about the massive ones. So these ones, the massive ones, we can integrate out and keep the massless ones, which are these. These are described massless particles in 10 dimensions, and we can describe them by fields. So they correspond to fields in 10 dimensions. That's why in most computations involving ADS-CFT, all we care about is these fields in 10 dimensions. So let me write that down. So the 10D fields that correspond to the massless string modes would be the metric, 10D metric, and there's other things. There's like a scalar, dilaton, there's like a 2 form or B mu nu, and there's others. I'm not going to write it down, but the important fact is that one of the fields, one of the corresponding to massless string modes, is the metric, and this 10-dimensional theory would be a gravity theory. So the action at low energies of this 10-dimensional theory is, so at low energies, we get a 10-dimensional gravity theory. Well, in this case, if we're doing superstring theory, then it would be supergravity with some Newton constant. G in 10 dimensions. Well, I can write the 1 over 16 pi g, the thing that appears in the action, to note the G in 10 dimensions by G10. And it's related to the string length and the string coupling. So it's 2 pi divided by 2 pi times the string length to the 8th power times G string squared. And what does the action look like? The action looks like, well, Einstein gravity plus various other things that are required by supersymmetry. So the action in 10 dimensions, 1 over 16 pi g in 10 dimensions times Einstein-Hilbert term. And then there's other terms that involve the other fields. So this is what happens at low energies. But at low energies, after we integrate out the massive string modes, we get an effective action. So this is just the first term in a derivative expansion. In addition to this, there are also terms with larger number of derivatives. But as I said, we're going to work in the limit in which those higher derivative terms would be negligible. I'll mention what they are later. Okay, good. So what I want to tell you next is where this, just to give you a rough idea of where this ADS space comes from and where the gauge gravity duality comes from in string theory. And then the plan was to do a specific, to do an explicit computation using ADS-CFT, computing how to use ADS-CFT to compute the potential between a quark and an anti-quark. Does that sound like a good plan? Yes, no, maybe? Okay, good. So this ADS5, I'll just focus on the example that I said was understood the best, worked on the most, which is this duality between ADS5 times S5 and n=4 superang mills. So for ADS5 times S5, so where does ADS5 appear in string theory? Because what I said so far about ADS is that, okay, it's a nice space, it's got constant negative curvature, it solves Einstein's equation with negative cosmological constant, but when I wrote down this 10-dimensional action, there's no negative cosmological constant. So where does that come from? And the answer is that we need an extra space, an extra factor, which is S5s to make a 10-dimensional space. And then ADS5 times S5 solves the equations of motion of this 10-dimensional action, the 2B supergravity. Well, there's other fields, but the important part is that there's a 10-dimensional metric, which is ADS5 metric. And then there's a 5-sphere, also of radius of curvature L. So the metric is just a product, well, the sum of the metric on ADS5 and the metric on S5. For here, I wrote down, for S5, I wrote down ds S5 squared means the metric of a unit radius sphere. So if I put L squared up front, this would be a sphere of radius L. What I mean by this formula is that the radius of ADS5 here is L, and the radius of S5 is also L. They have equal radii. And then there's other fields. As I mentioned, there's other fields in 10 dimensions, and one has to say what those fields are too in order to have a solution. No, we actually have to solve some equations. I'm not going to solve the equations, but I'm going to say just one thing, that there's also, in 10 dimensions, there's also a 5-form. Field strength is the field strength of a gauge field, and this is proportional to some n times the volume form on ADS5 plus the volume form on S5. And also the dilettante can take any value. That's all we need to know about this. We can already, sorry, one more thing. In order for this to be a solution, one requires this relation. L to the 4th times this string length to the 4th power is 4 pi times G string times n. This n will be the end of the gauge theory, but not yet. From here, we can already see when gravity is a good approximation. For gravity with 2 derivatives to be a good approximation, what should happen? Curvature should be small. So here, the radius of curvature of ADS is L. So L being small means, curvature is small, the radius of curvature is L. L has to be large. So this space is weakly curved. if L is large in what units? String units is an option. What other units are natural in the theory of gravity? Planck units. How do we figure out the Planck length? From G10, what is the Planck length? Ls times GS to the power 1/4. So L divided by Ls is GS to the power 1/4. So this is much smaller than 1. If we want the strings to be small, we want L to be big in the string units as well. Oh, sorry, much bigger than 1. I'm sorry. And this implies, based on that formula, that N is much bigger than 1. So that's the condition, that the field theory has a large number of degrees of freedom. Okay. So now, just one more thing about this, and then we'll just move on to the field theory side. So there's actually a more general, something more general. A more general solution that one can write down in string theory, and this will be relevant for Igor's talk this afternoon. So this geometry, ADS 5 times S5, is a limit of a geometry of a different geometry created by a stack of D3 branes. So, okay, string theory has strings, but it also has branes, and D branes are hypersurfaces. You can think of them as hypersurfaces on which strings can end, and they're very heavy objects. So the idea is that we can have a stack of n of them, and because they're heavy, D3s, because they're heavy, they curve space-time around them. So a D3 brane is a heavy object with tension. It's not the tension, TD3 is 2 pi over 2 pi L string to the 4th times G string. And they create a 10-dimensional metric. So D3 are 3 plus 1 dimensional objects with 3 space 1 time. And if they're flat, the 10-dimensional metric they create is this. So H of R to the minus 1/2 minus dt squared plus dx squared plus H of R to the power 1/2 dr squared plus R squared, the metric on S5. Sorry, X is just 1 to 3, X1, X2, X3. No. Yeah, so this is the parallel space to the brane, which is R3, 1. And this is the transverse space, which is just R6. So we're 4 plus 6 is 10. So it's good. We're in 10 dimensions. And this function H is 1 plus L to the 4 over R to the 4. And then one can show that if we take a limit of this more general, so this is also a solution to the equations of motion of the 10-dimensional action over here. And if we take a limit of this solution, we get ADS 5 times 5. That's the relation between them. So if we zoom in close to the branes, then that space is ADS 5 times 5. Otherwise, this space that's created by the branes is asymptotically flat because this function H goes to 1 at infinity. So when we're very far from the branes, so r is the distance away from the branes. When r is very large, then this h is 1, and the space just becomes flat 10-dimensional space. Then it, of course, gets curved and very close to the brane. So if we zoom in close to the branes, we're essentially ignoring, I mean, one can do this more rigorously, but we're essentially, if we zoom in close to the branes, we're essentially ignoring this one from here. And then what the space becomes, it becomes, so the metric is approximately, so h becomes L to the 4 over R to the 4. So h to the minus a half is R squared over L squared times minus dt squared plus dx squared. And then from that part, we just have h is square root of h is L squared over R squared. So we have L squared over R squared dr squared. And in the second term, R squared cancels. So we just have L squared times the metric on the unit sphere. This doesn't quite look like the way I wrote ADS5, but this is ADS5. If we further make a change of coordinates, z is L squared over R, then this space here is just L squared over z squared times minus dt squared plus dx squared plus dz squared plus L squared times the metric on S5. One reason why I did this is because this provides a generalization of ADS-CFT, of the instance of ADS-CFT that I'll describe. For example, we can replace this transverse space with other spaces, and then we obtain something else here, and this would be relevant for Igor's talk. And then instead of S5, there will be some other 5-dimensional space. And that will generate other theories, not n equal 4 superangles. Say again. The symmetry, if you're not close to the, yeah, because they break the 10D Lorentz symmetry. The 4D one is still present in this more general solution. What's not present is this SOD comma 2. SOD comma 2 emerges only when we take the limit when we go close to the branes. Okay, good. So that's roughly what I wanted to say about this. So now very briefly about n equal 4 superangles. Where can I write? Maybe I can start over here. So I'm not going to describe in detail. So on the gauge theory side of the correspondence for ADS5 times S5, we have n equal 4 superangles. I'm not going to describe in detail what it is, but it's a gauge theory. We can take the gauge group to be SUN. And the way it appears in this picture with the D3 branes, that we can have open strings ending on the D3, starting and ending on the D3 branes. And this is n equal 4 superangles is the theory at low energies that's described by these open strings. And that relation gives that the string coupling is G(n) mil squared over 4 pi. So what's the field content? Well, it's a gauge theory, so it has to have a gauge field. So there's a gauge field A mu. Transforms in what representation of SUN? Adjoint representation, good. And the theory has n equal 4 supersymmetry. So it also contains all the other fields that are necessary to have n equal 4 supersymmetry. So those are some fermions and 6 scalars. So it has some fermions. Where this index A goes from 1 to 4, and alpha dot go from 1 to 2. They're the spinor indices, so they're like 4 different species of fermions, and 6 types of scalars. So xi. Well, these x's are not the same as the x's, the embedding coordinates of ADS. So here I goes from 1 to 6. And so this is the content of a vector multiplet. And this theory, in addition to, well, there's gauge symmetry, but it has other symmetries. One symmetry that it has is an SU4 global symmetry called SU4R or SO6. So these scalars, the 6 scalars transform under this symmetry, and the fermions do too. And SU4 is the same as SO6. And the way that fits with this picture is that the SO6 is the symmetry group of the S5. Okay. And there's some action. And let me write it down. I guess I could. So the action is 1 over 2 GML squared d4x raised f mu nu f mu nu. And then there's other things involving these other fields, the scalars and the fermions. So there's a kinetic term for the scalars, d mu x, d mu x. By the way, the scalars and the fermions also transform in the adjoint of the gauge group of SUN. Then there's a potential for the scalars, xi xj squared. There's a kinetic term for the fermions. I'm just going to write it schematically. And there's also Yukawa couplings. Whatever this action is, it is determined uniquely by having this amount of supersymmetry. So one can derive it just based on that. Write down the first term, and then the rest are required by supersymmetry. Okay. So what are the parameters? The parameters are n, the rank of the gauge group, and g angles. One can also introduce a theta angle, but let's not worry about that for now. And the main thing about this theory is that it's exactly conformal, meaning that the beta function for the coupling, g angles, is 0. The coupling does not run in this theory, the Yang-Mills coupling. It's a true parameter of the theory. Good. So I described ADS and n equal 4 super Yang-Mills. So then what's the relation between them? That's a statement of the duality. So ADS CFT. That's n equal 4 super Yang-Mills. Dual to string theory on ADS 5 times S5. And the relation between the parameters is this. Well, I wrote it down already. One relation is that the G string is G Yang-Mills squared over 4 pi. And the other relation is also written on the board there. L to the 4th over L string to the 4th, L over L string is 4 pi G string times n, everything to the 1/4. There's a relation on the top board on the right. The 4 pi times g string is g n mil squared. So this is just g n mil squared times n to the power of 1/4. In which limit is this duality useful, where we can use supergravity in the bulk? Well, in the limit where the space is weakly curved, so that means n is bigger than 1. And if we want the strings to be small, much smaller than the size of the space, then we also want g n mil squared times n, which is the 't Hooft coupling, to be much bigger than 1. So classical gravity requires n much bigger than 1. And if we want to have the strings to be small as well, we could have g n mil squared and also be much bigger than 1. So that's why this duality is useful for a strongly interacting gauge theory. Okay. Any questions? So then I wanted to do a computation just to see how it could potentially be useful. So let's try to compute. And I'll tell you what the rule is. Compute the quark-antiquark potential and using ADS-CFT. So the claim is that for various quantities that we want to compute in the n equal 4 superannuals theory, there's some corresponding computation. If we want to compute it as strong coupling and large n, there's a corresponding computation that we should do in the bulk on the gravity side. So let me show you this computation for the quark-antiquark potential. So application. Question, how do we compute the quark-antiquark potential in general? What do we compute? Expectation value of Wilson loop. So the expectation value of the Wilson loop would be, if we consider a loop that's like very long like this, corresponds to a quark and an antiquark moving in time, separated by some distance. And this would be in Euclidean signature. This will be e to the minus the potential times the time. So the rule for computing this in ADS-CFT is this. We start with this ADS space and consider on the boundary this Wilson loop. I'm going to write it, I'm going to draw it as two parallel lines. So one the quark and the other one the antiquark. And then the rule is, maybe I can just draw them farther apart so I have more room. And then the rule is to figure out a string world sheet that ends on this contour. Hopefully the picture's clear. So it's just a string that dips a little bit into the bulk. The distance between these is r. And the rule is that the expectation value of the Wilson loop is the partition function of the string, which can be approximated by let me write that. Can be approximated by e to the minus the action of the string. It would be a semi-classical, a saddle point approximation. ADS-CFT. there's various rules for computing various things. This is a rule for computing this observable. So this is Z string. Z string is the integral over the string worldsheet, e to the minus the action. By a saddle point approximation, this is e to the minus the classical value of the action for the shape of the worldsheet that minimizes the action. So with a boundary condition that the boundary of the surface of the string worldsheet is the contour in the gauge. Of course, I cannot reach it. I want to denote the string worldsheet by sigma, and then the curve on the boundary. This would be C, and this would be sigma. So the boundary of sigma would be C. So how do we do that? So the string action is 1 over 2 pi alpha prime times the area of the worldsheet. We can parameterize the worldsheet with 2 coordinates, tau and sigma. And we have to include square root of the determinant of the induced metric. Now, if we take this tau coordinate to be the space-time time coordinate, and sigma to be x, x being the direction along the boundary. So this would go from 0 to r. Then for this shape, z is a function of x that we need to find. We need to find it, and then we have to plug it back into that formula and figure out what S is. So let me write down a couple of intermediate steps, maybe not many. Maybe I want it higher. I was going to spend most of my time raising and lowering the boards. Okay. The point I want to make with this is that the computation is really like a, classical mechanics problem. But let me write it in that form. So the induced metric can be computed from plugging in that parameterization in the ADS metric. So this would be L squared over Z squared times, in Euclidean signature would be dt squared plus dx squared. And instead of dz squared, because z is a function of x, this would be z prime squared, where prime is a derivative with respect to x, times dx squared. So this means that the determinant of the induced metric is square root. So it's this, whatever multiplies dx squared, square root of that, times whatever multiplies dt squared, square root of that. So it would be 1 plus z prime squared over z squared times L squared. And the action, I can write it here, is 1 over 2 pi alpha prime times L squared times the integral from 0 to r dx square root of 1 plus z prime squared over z squared, where z is a function of x. And here we can integrate the time coordinate when we get the total time, which is capital T. So the rule is to extremize this, meaning find the z of x that extremizes it with boundary conditions that z of 0 is 0 and z of r is also 0, meaning that the surface is anchored on the boundary. And then you can use the usual tricks from classical mechanics. This action is independent of, the Lagrangian is independent of x. If we think about x as a time coordinate, then that means that the corresponding Hamiltonian is conserved. We can use that conservation law to find an equation, a first order equation for the shape of the worldsheet. And then we can just plug it back in. So I can just tell you what the answer is. If people want more intermediate steps, I have them. So the answer, maybe I'll write here. They represent something only in terms of the string worldsheet that dips down. So I have z as a function of x. So maybe the picture isn't clear. So we have, I can describe this shape if I have some coordinate here, x, that runs in this way. I can have z as a function of x that says exactly where this surface is. When x is 0, z should be 0. When x is r, z should be also 0. That's what the boundary conditions are. Does it answer the question? So the answer is, well, if you do the calculation, this is the answer that you'll find. You'll find that the, so S is the integral from, well, you'll find that the end, you'll find that the answer actually diverges because the space is infinite close to the boundary. It's because of the factor of 1 over z squared in the metric. Yeah, so it's better to just, instead of going all the way to z equals 0, to go to z equals epsilon. So cut off at z equals epsilon. Then the action will be t L squared over pi alpha prime times 1 over epsilon minus, you can write the same kind of epsilon, minus 4 pi cubed over gamma to the 1/4 to the 4th power times 1 over r. So then, question, why is there a divergence? It's infinite volume near the boundary. So what does the divergence mean?
Normalization.
Yeah, so we can, in order to make this Wilson loop, we can have a quark that's actually moving along that trajectory. And this would be the energy of that quark. And the quark is infinitely massive. Another way of saying it is that whenever we define a line operator like a Wilson loop, we can always add to it a term proportional to the perimeter of the loop. That there's a choice of scheme for defining the operator. So this 1 over epsilon here, even though it blows up, that's its interpretation. So the quark antiquark potential is actually given by the second term. So this would be, if we then translate it, L squared and alpha prime to gauge theory quantities, this would be square root of g ml squared n times 4 pi squared over gamma of 1/4 to the 4th power times 1 over r. Is the 1 over r expected? Yes, it's a Coulombic potential. It follows from the fact that the theory is conformal. But the coefficient is given by this. Now, maybe one more question, and then I'll finish. How does this compare to weak coupling? So if I have electromagnetism at recoupling, what is the potential between two charges? E squared over 4 pi r. If we set epsilon naught to 1, it's minus E squared over 4 pi r. Then in Yang-Mills theory, if we're at recoupling, what is the potential? No, also between a quark and an anti-quark. Oh, I'm sorry. It was over there. Yeah. So compare to recoupling. So at recoupling, V of R is approximately, so in electromagnetism, E squared over 4 pi r. Yang-Mills theory, minus G Yang-Mills squared over 4 pi r. But there's an extra factor. N squared minus 1 is a guess. Are there any other guesses? N squared minus 1 over n is a better guess. Any better guesses? N squared minus 1 over 2. So why is that? That's a quadratic Casimir. So the charge squared from electromagnetism is replaced by the quadratic Casimir of the representation, and this is a quadratic Casimir of the fundamental representation. Showing this is actually a homework problem in Peskin and Schroeder. It's problem 15.3. So for example, in QCD for 3 colors, this is a factor of 4/3. So maybe I can stop here, continue next time.
Of the divergence, you have some choice of to say that instead of subtract 1 over epsilon, subtract 1 over epsilon plus some confinement, we get some potential of long distances. What would be the
computation that I did, you can't see the resolution of this, but the divergence is proportional to the perimeter. So you can subtract something proportional to the perimeter. And that what that does to the potential is just adds a constant. So what you conclude is that the potential could be this plus a constant, but we know that you can always add a constant to the potential. Sorry?
Nothing depends on it, or
So far, no. If we work at large n and large Topf coupling, so G Yang-Mills squared n is large, then nothing depends on the theta angle to all orders in perturbation theory in 1 over the Topf coupling. We could consider not large Topf coupling. We could consider a limit where n is large and G Yang-Mills is fixed. If we consider such a limit, then the theta angle will also be important.
So you went from ADS to its covering space motivated by the fact that I think in our theory of gravity we would not like to have the closed time-like curves. But from the point of view of this duality, would duality still hold if we stay in the original ADS space? And what would there be a meaning to this in the dual CFD?
You mean in the one with the closed time-like curve?
Would there be a meaning to the closed time-like curve?
Well, I don't know what the interpretation of that would be. I believe that it's probably something would go wrong with if we consider string theory in the background like that. I'm not sure. Yeah.
Don't we have a term in the metric corresponding to the S5 part of the metric? Why are we?
Why are we doing this Wilson loop computation? Well, we can also, yeah, so to be precise, I have to say what happens with the Wilson loop, with a string in 10 dimensions, not in 5 dimensions, and I was not precise about that. So one thing one can do is to take the string to lie at a fixed point on the S5, and then it would not move in the S5, it would not contribute to the action. However, that would not correspond to the pure Wilson loop that I wanted to compute. It would correspond to the Wilson loop with an extra coupling to scalar fields. However, the difference between that Wilson loop and the Wilson loop that I wanted to compute with no extra scalar fields is subleading in 1 over lambda. So at leading order, there's no difference. Yeah, but one has to be precise about that. And I think there's an interesting story that's actually not completely figured out. How to deal with a Wilson loop that has the extra scalars, where the string sits at a fixed point, and the Wilson loop that doesn't, and I don't know what other possibilities there might be.
Okay, let's thank Silviu again.